Before the first stars, there was only darkness. A darkness without shape or shadow. A silence so deep it could swallow all sound. The universe was young then, only 380,000 years old. An infant in a life that would stretch for billions of years. In that young cosmos, matter and light were bound together in a blinding fog of energy. Photons, the particles of light, could not move freely. They ricocheted endlessly among a sea of charged particles, trapped in an eternal scattering. Then, in a single cosmic moment, the universe cooled enough for atoms to form. The fog cleared, and for the first time since the beginning, light broke free. These first photons began a journey that has never ended. Across expanding space, through the rise of galaxies and the death of stars, they have traveled. They carry with them the memory of the universe's birth, a message written before there were planets, before there was Earth. Each ray is a letter written in the handwriting of creation. And only now, after 13.8 billion years, are we learning to read them. This light is called the cosmic microwave background. It is not only ancient, it is the oldest light that will ever exist. Still, it falls upon us every second from every direction in the sky. A relic from the moment the universe first became transparent. And within its faint, uniform glow lie secrets powerful enough to challenge the very framework of cosmology. The oldest light is speaking. The year was 1964. On a rise of grassy farmland in Homedale, New Jersey, a peculiar structure stood against the spring sky. An enormous, white-painted horn, 6 meters wide at the mouth, tapering into a narrow throat that bent into a squat, box-like building. Its metal skin gleamed faintly in the morning sun, streaked with rivets and seams, a relic of Cold War engineering. It had been built for a very different frontier, not to explore the universe's birth, but to carry human voices across oceans. The Homedale horn antenna was designed by Bell Telephone Laboratories as a receiver for the first active communication satellites, listening for faint microwave signals beamed from the newly launched Telstar. The structure's flared, horn-shaped mouth was not for beauty, but for precision. It was shaped to eliminate stray reflections, to swallow up all radiation within its field of view and direct it cleanly into the detectors inside. In this place, two young radio astronomers, Arno Penzias, a German-born physicist who had fled with his family from the rising tide of Nazi power, and Robert Wilson, a Texan with a sharp mind for instrumentation, were working on what they thought was a routine calibration. Their goal was simple: to measure and remove every trace of noise from the antenna's readings so that future experiments could be as clean and accurate as possible. But the sky they listened to would not fall silent. The noise came as a faint hiss, a steady, featureless background that persisted no matter where the antenna was aimed. It was not the static of a passing aircraft, nor the bright pulse of a radar station, nor the erratic flicker of distant thunderstorms. It was everywhere, in every direction, at all hours, with the same intensity whether the horn was pointed at the Milky Way's core or out into the darkness between the stars. First came suspicion. Perhaps this was the fault of the electronics, a malfunction in the amplifiers, a quirk in the detectors. The men replaced components, tested circuits, and measured the instrument's thermal background to a precision unheard of in microwave astronomy. Still, the hiss remained. Then came the more earthly possibilities. Could it be a reflection from the ground, or a transmission from a distant city? The Homedale site was relatively isolated, but not immune to the invisible web of radio traffic blanketing the eastern United States. Penzias and Wilson made careful measurements at different angles and times of day, looking for variations that might betray a local source. There were none. The last suspect was almost comical: life itself. Pigeons had taken to roosting in the warm metal shelter at the horn's narrow end, leaving behind a soft white coating of droppings that, in the polite language of their research notes, they called a dielectric material. The birds were gently trapped and released several miles away. The antenna was scrubbed clean. The hiss did not change. Unbeknownst to them, just 60 kilometers away at Princeton University, another group of scientists was preparing for a very different kind of hunt. Robert Dicke, a physicist whose work spanned gravitation and cosmology, was leading a small team intent on finding something predicted nearly 2 decades earlier by George Gamow, Ralph Alpher, and Robert Herman: the cooled afterglow of the Big Bang. Gamow's generation had reasoned that if the universe had once been a hot, dense plasma, then as it expanded and cooled, there would come a moment when matter and radiation parted ways, when photons could finally travel freely through space. Those photons, stretched by billions of years of expansion, should now fill the cosmos as a faint glow in the microwave region of the spectrum. No one had yet found it. Dicke's group had designed a sensitive microwave detector to search for exactly that signal. They had not yet begun their survey when a phone call arrived from Bell Labs. Penzias, puzzled by the hiss he could not remove, sought the advice of Bernard Burke, a mutual acquaintance who knew of Princeton's work. Soon, Penzias and Wilson were in contact with Dicke's team. When Dicke hung up the phone after hearing the Holmdel results, he turned to his colleagues with a wry smile and said, "Well, boys, we've been scooped." The hiss was not noise. It was the oldest light in existence, the cosmic microwave background. Each photon in that signal had been traveling for nearly the entire history of the universe, set free just 380,000 years after the Big Bang, when the first atoms formed in space became transparent. What Penzias and Wilson had stumbled upon by accident was the very phenomenon Dicke's group had set out to find by design. In the weeks that followed, the two teams published back-to-back papers in the Astrophysical Journal, one reporting the detection, the other explaining its significance. Neither paper used dramatic language. Yet in those measured lines of technical prose lay a profound transformation of cosmology. The CMB was proof that the universe had a fiery origin, that it had expanded and cooled from an earlier, hotter state. What no one yet knew was that the apparent smoothness of that glow would conceal a paradox, one that would upend the understanding of time, causality, and the shape of reality itself. But for now, the door to the deep past had opened, not with a blinding revelation, but with a steady hiss in the cold air over a New Jersey hillside. In the world of mid-20th century cosmology, the origin of the universe was an open battlefield. Two rival visions dominated the field. One was the steady-state theory, championed by astronomers like Fred Hoyle, Hermann Bondi, and Thomas Gold, a vision of a universe eternal in time, unchanging on the largest scales, where new matter was continuously created to fill the gaps left by expansion. In such a cosmos, there was no beginning and no end. The universe had always been and would always be. The other was the Big Bang model, a term Hoyle himself had coined with a hint of derision during a BBC radio broadcast in 1949. It described a cosmos that began in a hot, dense state and had been expanding ever since. This idea had roots in the equations of general relativity, in Edwin Hubble's 1929 discovery of the galactic redshift, and in the earlier theoretical work of Georges Lemaitre. But it remained speculative, a possible explanation, not a proven truth. By 1964, both camps had strong arguments and loyal adherents. Observations of distant galaxies confirmed that space was expanding, but did not reveal how it began. The steady-state theory explained this expansion without requiring a moment of creation. For decades, many astronomers had found its eternal stability appealing. A universe without an origin was less burdened by metaphysical questions. Then came the hiss from Holmdel. When Arno Penzias and Robert Wilson described their uniform, directionless microwave noise, and when Robert Dicke's team realized its implication, it was immediately clear. The signal was exactly what the Big Bang model had predicted. If the universe had once been much hotter and denser, then as it expanded and cooled, the light from that early era would be stretched into the microwave band. The CMB was the smoking gun. It was not simply that this faint radiation existed. It was that it was everywhere, with a temperature just under 3 Kelvin, only a few degrees above absolute zero, and astonishingly uniform across the entire sky. The detectors at Holmdel saw no difference whether they were pointed toward the galactic center or toward the far reaches of intergalactic voids. This uniformity was as much a shock as the detection itself. In the steady-state model, there was no mechanism to fill the universe with such radiation. The only plausible origin was a hot, dense phase in the remote past. Exactly the scenario steady-state theory denied. Within a few years, the majority of the scientific community shifted toward the Big Bang as the dominant framework for cosmology. But the shock ran deeper than a shift in theoretical preference. The CMB was a time machine. Each photon that Penzias and Wilson had detected was an ancient messenger, launched when the universe was only 380,000 years old, an era when there were no stars, no galaxies, not even the elements that would later form planets and life. The cosmos then was a smooth sea of hydrogen and helium atoms, bathed in a uniform glow. In a sense, astronomers were not just seeing across space, they were looking directly into the deep past. The CMB was the first direct evidence of what the infant universe looked like, a snapshot preserved for 13.8 billion years. Before that moment of last scattering, when photons first traveled freely, the universe was opaque, a hot fog of plasma in which light could not escape. This sudden unveiling marked the beginning of cosmic transparency. And yet, even in those early days of study, there was something unsettling. The radiation's near-perfect smoothness implied that distant regions of the universe, separated by billions of light years, had somehow reached the same temperature, as if they had been in contact. But according to the rules of relativity, light and information can only travel at finite speeds. There simply had not been enough time, since the Big Bang, for those far-flung regions to exchange heat or coordinate their temperatures. This was the horizon problem, and it posed a fundamental question. How could the universe be so uniform in places that could never have influenced each other? At the time, no answer was known. Some argued that the smoothness was a coincidence. Others suggested that the laws of physics themselves might differ on the largest scales. A decade later, a radical idea called cosmic inflation would attempt to solve the puzzle, proposing that the universe underwent a brief, violent burst of exponential expansion in its earliest fraction of a second. But in 1964, this was still far beyond imagination. The scientific shock of the CMB was therefore twofold. First, it forced a surrender of the steady-state model. The universe had a beginning, and it had been hot. Second, it confronted cosmologists with a deeper paradox, that the cosmos appeared too coordinated, too perfectly balanced for the laws of physics as then understood. From the perspective of philosophy, this was equally profound. If the CMB was the afterglow of creation, then the night sky was no longer an empty darkness scattered with stars. It was filled with the silent memory of the beginning, a background hum of existence itself. Every point in space carried the same ancient signature, as if the universe was reminding itself, everywhere and at all times, of how it began. In the years following the discovery, the shockwaves spread outward. Satellite missions were proposed to map the CMB with greater precision. Radio observatories began to tune their instruments not just for transient bursts or galactic emissions, but for the subtle patterns in that microwave haze. The faint hiss from Holmdel had revealed the most enduring relic in all of physics, a whisper older than the oldest galaxies, still crossing the universe, still falling on every square centimeter of space, including the one where you sit now. And this, perhaps, was the most humbling part of the shock, that the signal was never hidden. It had been all around us, always, washing over the Earth since before the Earth existed. It required no exotic lens to see, only the right kind of listening. The hiss from Holmdel had shattered an old vision of the cosmos, but in many ways, the real work was only beginning. A discovery is not an answer, it is a doorway. And the doorway Penzias and Wilson had opened did not lead to a small, neat chamber of explanation. It opened onto an immense, unlit hall, whose walls were invisible and whose echoes seemed to come from the birth of time itself. The task before scientists now was to chart that haul. In the months after 1964, astronomers across the world began to turn their radio antennas toward the microwave background. The goal was simple: to measure it more precisely, to map its temperature, and to determine whether the faint glow was truly as uniform as first believed. If any variation, any slight brightening or dimming, could be detected, it might reveal the seeds from which all cosmic structure had grown. But the challenge was daunting. The signal was weak, just a few thousandths of a degree above absolute zero. It was also constant, unblinking, unchanging, indifferent to the motion of the Earth. To study it meant learning to strip away all other sources of microwave radiation. The hiss of our own galaxy, the noise from the sun, the emission from nearby gas clouds, even the microwave leakage from the atmosphere itself. For nearly 2 decades after its discovery, the CMB seemed stubbornly featureless. The most sensitive ground-based and balloon-borne experiments could find no irregularities. The background appeared smooth to 1 part in 10,000. This was beautiful, but also troubling. If the early universe was perfectly uniform, how had gravity sculpted it into a landscape of galaxies, stars, and planets? Somewhere, hidden in that smoothness, there had to be fluctuations, tiny density differences that would one day collapse into the cosmic web we see today. In 1989, the search was handed to the first satellite dedicated to measuring the CMB, COBE, the Cosmic Background Explorer. Launched by NASA, COBE carried 3 instruments, each designed to probe the microwave sky with unprecedented sensitivity. One of them, the differential microwave radiometers, was tasked with detecting temperature differences as small as a few tens of millionths of a degree. If there were primordial seeds imprinted in the radiation, COBE would see them. Another instrument, the far-infrared absolute spectrophotometer, FARAS, would measure the spectrum of the background, essentially the distribution of photon energies, to determine whether it truly matched the predictions of a blackbody cooled by 13.8 billion years of cosmic expansion. When the first results were announced in 1990, the scientific community was stunned. FARAS had measured the spectrum of the CMB with such precision that the data points lay exactly on top of the theoretical curve for a perfect blackbody at 2.725 Kelvin. Not close, not within the margin of error. Perfect. It was, in the words of COBE scientist John Mather, the most perfect blackbody spectrum ever measured in nature. This was a triumph, confirmation that the radiation really was the cooled remnant of an early hot phase, not the product of some exotic local process. But the second part of COBE's mission would make history. In 1992, the satellite revealed faint, irregular blotches across the microwave sky, the long-sought anisotropies, temperature variations of only about 30 millionths of a degree. These were the imprints of density differences in the early universe, the seeds from which all structure would form. George Smoot, the project's lead scientist, described them as the fingerprints of God, a phrase that made headlines but also captured the awe felt by those who had waited decades for this moment. The cosmic background was no longer a bland, featureless haze. It was a textured tapestry, its patterns frozen from a time when the universe was younger than 1 million years. By studying these patterns, scientists could read the physics of the early universe as clearly as archaeologists reading the inscriptions on ancient stone. The discovery triggered an explosion of new measurements. In 2001, NASA launched the Wilkinson Microwave Anisotropy Probe, WMAP, capable of mapping the CMB with far greater resolution. Over 9 years of observations, WMAP refined the age of the universe to 13.77 billion years, determined that it is spatially flat to within a tiny margin, and measured the proportions of its contents. About 4.6 ordinary matter, 24 dark matter, and nearly 72 dark energy. Every percentage point in those numbers had been teased out of the faint mottling in the microwave glow. The CMB had become the single most powerful dataset in cosmology, and yet deeper measurements revealed puzzles. There appeared to be a strange cold spot, a region of the sky several degrees across, slightly cooler than surrounding areas, more so than expected from random fluctuations. Some speculated it could be a statistical fluke. Others proposed it might be the imprint of a vast void in the large-scale structure, or even a hint of exotic physics, perhaps evidence of a collision between our universe and another bubble in a cosmic multiverse. More anomalies emerged. The largest-scale fluctuations seemed aligned along a particular axis, nicknamed the axis of evil, as if the entire sky were tilted in some subtle way. Such features were difficult to reconcile with the simplest models of inflation and early universe physics. By the time the Planck satellite released its final maps in 2018, the microwave sky had been charted with exquisite detail, down to angular scales less than 1/10 of a degree. The data refined cosmological parameters still further, confirming the flatness of the universe, the dominance of dark energy, and the near-perfect Gaussian nature of the fluctuations. But the anomalies persisted, like small imperfections in an otherwise flawless mirror. The deeper scientists looked, the more the CMB seemed to whisper two stories at once. One of remarkable agreement with the standard model of cosmology, and another of faint, lingering mysteries that might point beyond it. It was a paradox. The CMB was both the most precise, most well-understood signal in all of cosmology, and a source of unresolved questions that could one day upend our understanding of the universe. What began as a hiss in a New Jersey antenna had become the most profound map ever made, a cartography not of continents or oceans, but of time itself, plotted from the first visible moment the universe allowed light to escape. And still, across every patch of the sky, those ancient photons continue their journey, crossing the expanding gulf of space, carrying in their subtle variations the entire history of cosmic beginnings. The cosmic microwave background was supposed to be the universe's great reassurance, a pristine, statistical echo of its own infancy, perfectly predicted by theory and perfectly matched by observation. And in many ways, it is. Its black body curve fits so precisely to predictions that the mismatch is smaller than any measurement error humanity has ever recorded in nature. Its fluctuations, when plotted, align almost exactly with the statistical patterns expected from quantum ripples inflated to cosmic scales in the first fraction of a second. But for all its perfection, there is something unsettling in the CMB's face. Look closely, and the perfection begins to fracture. Tiny irregularities, small enough to hide in the margins, large enough to make cosmologists uneasy, begin to emerge. One of the most persistent is the so-called cold spot. It appears in the southern hemisphere of the microwave sky, a region several degrees wide, measuring slightly cooler than its surroundings. Not dramatically so, only a few hundred millionths of a degree, but significantly cooler than random chance would suggest. If the fluctuations in the CMB are like ripples on the surface of a cosmic pond, then the cold spot is like a deeper, darker hollow, as if something beneath the surface has drawn energy away. Several explanations have been proposed. One possibility is purely statistical. Perhaps by chance, a combination of smaller fluctuations happen to overlap, creating the illusion of a single, large anomaly. Another idea points to the Sachs-Wolf effect, in which light passing through a large underdense region, a cosmic void, loses energy, stretching its wavelength and cooling its apparent temperature. Surveys of galaxy distributions have indeed found hints of such a void in that direction, hundreds of millions of light-years across. But even this may not fully account for the cold spot's depth. Others have suggested more exotic origins. In some inflationary models, our universe is just one bubble in a vast, inflating multiverse. If two such bubbles collided in the early moments after their formation, the impact could leave a scar imprinted on the microwave background, a bruise in the afterglow of creation. The cold spot, they say, could be such a bruise, the signature of a universe we can never see directly, but whose shadow falls across our sky. If that were true, it would mean the CMB is not just a record of our own cosmic birth, but a meeting point between entirely separate realities. And the cold spot is not alone. When the Planck satellite examined the largest scale fluctuations, those spanning the greatest stretches of the sky, it found something stranger still. They appear to be aligned along a single preferred direction, an axis cutting across the universe. It was as though the cosmos, in its earliest moments, had been tilted. Theorists call it the axis of evil, partly in jest, partly in unease. The simplest models of inflation predict that the largest scale fluctuations should be randomly oriented, their directions entirely uncorrelated. An axis suggests some kind of large-scale structure, a cosmic asymmetry written into the very first quantum fluctuations. Is it real? Or is it an artifact, the result of subtle errors in foreground subtraction or some unrecognized bias in our instruments? Some scientists caution restraint, noting that the human mind is an expert at finding patterns in noise. Others suspect that the axis, the cold spot, and other anomalies, hemispherical asymmetries, unexpected alignments, may all be whispers of physics beyond the standard model. The unsettling thing is that these features, if real, would not just tweak our understanding of the early universe. They would demand a rewriting of the opening chapter of cosmic history. Inflation, that rapid, exponential expansion that supposedly smoothed the early universe, is meant to erase all such asymmetries, stretching any irregularity beyond the observable horizon. Yet here they are, staring at us from every all-sky map we've made. Some alternative theories propose that inflation itself was anisotropic, that it expanded faster in one direction than another. Others invoke cosmic topology. Perhaps the universe is not infinite, but wraps around on itself in subtle ways, producing alignments that mimic an axis. Still more radical are ideas of pre-Big Bang physics, that our universe may have inherited its structure from a prior state, perhaps a collapsing phase of an earlier cosmos, leaving ghostly imprints in the microwave background we now observe. The deeper we probe, the more the CMB feels like a message we can almost read, but never entirely decode. And there's another tension, the Hubble constant, the rate at which the universe expands. Measurements of this constant from the CMB, using Planck data and the standard cosmological model, yield one value. Measurements from nearby galaxies and supernovae yield another. The difference is small in absolute terms, but statistically, it is becoming impossible to ignore. If both measurements are correct, then something fundamental in our cosmology is missing. The early universe, as told by the CMB, may not evolve into the present-day cosmos as simply as we thought. Some physicists have speculated about new forms of dark energy, interactions between dark matter and radiation, or changes in the laws of physics themselves in the epochs between recombination and now. The CMB has thus become not just a record of the past, but a detective's notebook, one in which some pages have been smudged, some overwritten, and some marked with faint symbols whose meaning is still unknown. In the darkness between the galaxies, that ancient light continues to stream toward us, untouched since the dawn. It crosses clusters and voids, threads through filaments of dark matter, and arrives in our instruments carrying both clarity and confusion. It is the universe's first photograph, but like any old photograph, it captures a moment without explaining it. We see the faces, the scenery, the frozen moment in time, but the story behind the image, the events that led to it, and the future it points toward, those remain hidden just beyond the edges of the frame. And as with any deep mystery, the more we focus on the image, the more its imperfections and subtle contradictions begin to dominate our attention. The CMB, once seen as the crown jewel of cosmology, now plays a double role. It confirms our most successful theories with unmatched precision, and at the same time, it dangles before us the possibility that those theories are incomplete, that the truth may be stranger than even our boldest models can contain. It is the light that gave us certainty, and it is the light that may yet take that certainty away. The cosmic microwave background is more than just a relic of fire. It is a code. Each faint fluctuation, each delicate rise and fall in temperature, is a letter in a script written when the universe was barely 380,000 years old. For decades, cosmology has been engaged in the slow act of translation. Some sentences in this ancient script are clear. Others are fractured, smeared, or written in a dialect we do not yet understand. To explain them, scientists have drawn from the most powerful ideas in physics, and at times from visions of reality that sound almost like myth. The most accepted framework is the lambda cold dark matter model, lambda CDM. In this picture, the universe is composed of ordinary matter, and dark energy. Inflation, an unimaginably brief burst of exponential expansion, stretches quantum fluctuations to cosmic scales, seeding the variations we see in the CMB. Over billions of years, gravity shapes these seeds into the vast web of galaxies and voids we observe today. In this model, the anomalies in the CMB are not forbidden, merely improbable. The cold spot, for example, might be a rare statistical outlier, the kind of accident that occurs naturally in a random field if one waits long enough. But probability is a subtle thing in cosmology. Our sample size is one universe, one CMB sky. Rare events cannot be averaged over in the usual way. They're either part of the script, or they're the script. Beyond the standard model, one of the most influential ideas is anisotropic inflation. In its simplest form, inflation erases all traces of directionality in the universe. But if inflation was not perfectly isotropic, if for some reason space expanded faster in one direction, then the largest fluctuations in the CMB would align, producing the so-called axis of evil. What could cause this? Some versions of string theory suggest that additional fields or dimensions could bias inflation, imprinting subtle asymmetries on the sky. Others propose that our universe may have been born spinning, its rotation imprinting a preferred axis on the CMB before inflation had fully smoothed it away. Another contender is cosmic topology, the idea that the universe may be finite yet unbounded, like the surface of a sphere or the inside of a torus. If space folds back on itself in certain ways, light from the early universe could travel along multiple paths, intersecting with itself and producing repeating patterns in the CMB. Detecting such patterns would be like finding the same face twice in a crowd photograph, proof that the scene wraps around in a hidden geometry. So far, no clear repeats have been found, but the limits of detection are close and the possibility remains. Then there is the void explanation for the cold spot. The idea is elegantly straightforward. If a vast underdense region lies between us and a patch of the CMB, the photons passing through it will lose energy as they climb out of its shallow gravitational well, the integrated Sachs-Wolf effect. This would leave the imprint of a cooler region on the microwave sky. Galaxy surveys have indeed found a supervoid roughly aligned with the cold spot, spanning hundreds of millions of light years. But simulations suggest that its effect is not strong enough to explain the full anomaly. Beyond these lies the more radical frontier, the multiverse collision hypothesis. In this picture, our observable universe is just one bubble in an eternally inflating sea. Each bubble is its own cosmos, with its own constants and perhaps its own laws of physics. If two such bubbles collided in their early growth, the boundary could leave a circular or elliptical scar on the CMB. The cold spot, in this view, is not an accident or a void, but a wound, a sign that our universe once brushed against another. It is a breathtaking possibility, but it carries a burden. To test it, we would need to identify more than one such scar, with patterns matching specific predictions from inflationary models. For now, the evidence is tantalizing but incomplete. Some speculate that these anomalies could be the echo of pre-Big Bang physics, structures that existed before our expansion began, perhaps in a contracting universe or in a timeless quantum state. In certain cyclic models, the universe undergoes endless sequences of birth, growth, and collapse. Each bounce leaves behind faint imprints in the next cycle's CMB, ghost patterns from a previous cosmos. Others reach into the domain of the holographic principle, the idea that our universe is a projection from information encoded on a distant surface. In such a framework, the anomalies in the CMB could be irregularities in that underlying code, glitches in the cosmic projection. Even within conventional physics, the CMB has become a key battlefield in the Hubble tension, the growing conflict between early and late universe measurements of the expansion rate. Planck's reading of the CMB under lambda CDM gives a Hubble constant around 67 kilometers per second per megaparsec. Local measurements, using Cepheid variables and type I supernovae, yield around 73. The gap is now wide enough, and the error bars narrow enough, that statistical flukes are unlikely. Possible resolutions include early dark energy, a brief phase of accelerated expansion between recombination and the present day, altering the sound horizon imprinted in the CMB. Interacting dark matter that exchanges energy with photons or neutrinos, subtly shifting the acoustic peaks in the CMB power spectrum. New relativistic particles, light species beyond the known neutrinos that influence the expansion rate in the early universe. Each of these would leave subtle fingerprints on the microwave background. Fingerprints Planck has already constrained, but not yet fully ruled out. Theories multiply because the CMB is unforgiving. It is not an abstract dataset, but a direct image of the universe's childhood, and any new physics must fit into that image without erasing its existing uncanny precision. To explain the anomalies without breaking the successes is a delicate art, like restoring an ancient painting without altering the brushstrokes that have survived for billions of years. And so, the CMB remains both a triumph and a challenge. Its uniformity tells us we understand the broad strokes of cosmic history. Its imperfections suggest there is something, perhaps many somethings, just beyond our grasp. In the glow of this ancient light, science walks a narrow path between certainty and wonder. Every anomaly is a crack in the door, but the door is heavy, and the hinges are set deep in the walls of space-time itself. If you want, I can now go straight into Chapter 7, Scientific Tools Ongoing Testing, which will detail the great cosmic machines, from COBE to Planck to the next generation of CMB observatories that are being built to read the last undeciphered lines of this ancient script. The oldest light in the universe is faint, so faint that its glow is just a few thousandths of a degree above absolute zero. It is invisible to the human eye, hidden in the microwave spectrum. To see it at all requires instruments of extreme precision, designed not only to collect this light, but to separate it from every other whisper in the cosmic air. In 1964, Arno Penzias and Robert Wilson stumbled upon it with a radio antenna meant for satellite communications. The signal was so overwhelming that it became a discovery. But from that moment onward, the challenge was no longer detection. It was detail. How finely could we read the map of this ancient sky? How deep could we dig into its texture without losing the story in the noise? The first great leap came in 1989, when NASA launched the Cosmic Background Explorer COBE. In its time, COBE was the most sensitive microwave instrument ever sent into space. It confirmed the CMB's blackbody spectrum with extraordinary precision, proving that the glow was indeed relic radiation from a hot, dense early universe. Its maps of the sky were crude by modern standards, smudged and blocky, but they revealed the first evidence of tiny fluctuations in the temperature of the CMB, differences of just 1 part in 100,000. These faint ripples would become the foundation of precision cosmology. A decade later came WMAP, the Wilkinson Microwave Anisotropy Probe. Launched in 2001, it orbited far beyond the Moon, where Earth's heat and radio chatter would not interfere. Maps were sharper, its vision clearer. Over 9 years, it measured the CMB with enough accuracy to pin down the age of the universe, 13.8 billion years, and to weigh the proportions of ordinary matter, and dark energy. MAP's data told a story of astonishing consistency. But even in that story were subtle hints of the anomalies. A low quadrupole moment, a strange alignment in the largest scales. The questions had not gone away. They had simply become clearer. Then came Planck. Launched in 2009 by the European Space Agency, Planck was the most sensitive CMB experiment ever built. It cooled its detectors to a fraction of a degree above absolute zero, scanning the entire sky in multiple microwave frequencies to strip away the interference of foreground dust and gas. Planck's vision was so sharp that it traced the minute acoustic peaks in the CMB power spectrum, the signature of sound waves rippling through the primordial plasma before recombination. These peaks told the story of the universe's earliest moments with a clarity never before imagined. And yet, in the fine print of Planck's maps, the anomalies persisted. The cold spot, the alignment of the largest modes, hemispherical power asymmetry. They were not artifacts of poor measurement. They were there, imprinted on the sky itself. But space missions are not the only eyes on the CMB. On the frozen plateau of Antarctica, where the air is dry and the horizon endless, the South Pole telescope peers into the microwave sky with a precision impossible from warmer, wetter places. At 10 meters in diameter, it could detect tiny distortions in the CMB caused by the gravitational lensing of galaxy clusters, mapping the distribution of matter across cosmic time. Nearby, the BICEP experiments, background imaging of cosmic extragalactic polarization, hunt for a different kind of signal, the faint, swirling patterns in the CMB's polarization that would be the fingerprint of primordial gravitational waves from inflation. Such a detection would not only confirm inflation, but open a window onto physics at energies far beyond what any particle collider could reach. In the Atacama Desert of Chile, the Atacama Cosmology Telescope scans the heavens from 5,200 meters above sea level. Its high-altitude site gives it dry, thin air, ideal for microwave observation. It has mapped the CMB with exquisite detail on small angular scales, probing the growth of structure and the subtle effects of dark energy. The next decade promises even sharper vision. Projects like CMB-S4, a planned array of telescopes across Chile and Antarctica, will push sensitivity and resolution to unprecedented levels. Thousands of detectors will work in unison, mapping the polarization of the CMB so precisely that even the faintest imprints of new physics might emerge. The Japanese Space Agency's Lightbird mission, scheduled for launch in the 2030s, will take to space to measure large-scale polarization with exquisite accuracy, searching for the B-mode patterns that inflation might have left behind. The stakes are not small. If primordial gravitational waves are found, they would be the first direct evidence of inflation, a discovery that would reach back to the first trillionth of a trillionth of a trillionth of a second after the Big Bang. If they are not found, some of the simplest and most elegant inflationary models may fall away, forcing cosmologists to explore stranger possibilities. Beyond inflation, the next generation of CMB experiments will test the very shape of the cosmos. They will measure the curvature of space with precision fine enough to confirm whether the universe is perfectly flat or subtly curved. They will hunt for signs of new relativistic particles, search for evidence of cosmic strings, hypothetical relics of symmetry breaking in the early universe, and refine the constraints on the sum of neutrino masses. Each of these measurements will be etched in the CMB's delicate patterns, waiting to be found by instruments sensitive enough to read them. But no matter how advanced the technology, one fact remains. The CMB is a finite resource. The photons that left the surface of last scattering have been traveling toward us for nearly 14 billion years. We have only one view of this sky. Once it is mapped to the limits of physics, the data will be complete. There will be no second chance. This is why every anomaly matters. Every hint of deviation from theory is a possible door to new physics, a door that might close forever if not studied with absolute care. In the frozen silence of Antarctica, in the thin air of the Atacama, in the black void of space, the detectors listen. They listen for patterns that should not be there, for whispers from other worlds, for the tremor of gravitational waves born before time had a name. The work is slow. Years pass between the gathering of data and the extraction of meaning. But in that slowness lies precision, and in that precision, the possibility of revolution. The most ancient light still crosses the universe. And as long as it does, humanity will keep building sharper eyes, colder detectors, and quieter places to listen. For somewhere in that light, the universe's first story is still waiting to be read to the end. In the cold silence between galaxies, the oldest light still drifts. It does not hurry. Its journey has already taken longer than the existence of every star we see. The photons of the cosmic microwave background began their voyage when the universe was young, when the first atoms formed and the first shadows fell. In that moment, space itself became transparent, and this light slipped free from matter's grasp. Since then, it has passed through eons as if through a dream, past the first stars igniting in dark oceans of gas, past galaxies taking shape from the slow choreography of gravity, past worlds where no eyes ever opened to see. It is not light in the way sunlight is light. It is colder, stretched by expansion until its wavelengths have grown 1,000 times longer than when it began. Yet, within it, the memory of that first fire is still intact. For most of the universe's history, no living thing knew it was there. It crossed billions of light years in absolute anonymity, spilling across empty space without purpose or witness. It did not fade, for space itself is without air or dust to absorb it. It simply traveled, carrying a map of the universe's earliest face imprinted across its surface. And then, on a small, warm planet orbiting an ordinary star, a new kind of matter emerged. Matter that could think, that could ask, that could build a machine to listen. In that moment, the light had found an audience. We often imagine that we discovered the cosmic microwave background. But perhaps it is better to say that the light discovered us, that after 13.8 billion years, it finally met something capable of hearing what it had been saying all along. This is the strange intimacy of cosmology. The most ancient signal in existence is also the most democratic. It falls on every place, every person, every mountain and sea. Even now, as you listen to these words, photons from the dawn of time are passing through your body. They will go on, crossing into the dark beyond, long after your atoms have joined the stars. For physicists, the CMB is data, an archive of temperatures, polarizations, and spectra. But beneath the mathematics lies a deeper story. The universe once burned, and we are its descendants. The patterns in the CMB are not random. They're the frozen shapes of sound waves that rippled through the primordial plasma, the echoes of pressure and gravity intertwined. Those patterns tell us not just how the universe looked, but how it behaved, and perhaps why it exists in this form at all. We do not yet know if the anomalies are whispers from before the Big Bang, or the fingerprints of physics beyond our current grasp. Perhaps they are signs that the universe is stranger, more layered than we can yet imagine. Or perhaps they are nothing, mere statistical accidents that mock our hunger for meaning. Science is an act of humility before the unknown. It is also an act of courage. To read the CMB is to look into a mirror older than time itself. It is to confront the fact that the universe has no obligation to be simple, comprehensible, or kind to our questions. It is to accept that the final answers may never arrive, and that the beauty lies partly in the chase. When Arno Penzias and Robert Wilson first heard the hiss of the CMB, they were searching for something else entirely. They did not expect to brush against the oldest thing in existence. That is the nature of discovery. It arrives sideways, unannounced, in the middle of an ordinary day. One day, perhaps, the anomalies will be explained. One day, perhaps, a new telescope will detect the unmistakable spiral of primordial gravitational waves, or the faint twist in polarization that confirms a multiverse beyond our own. Or perhaps the anomalies will deepen, splintering the standard model of cosmology into something stranger. But even if the light tells us everything, it will not be the end of wonder. Because the CMB is not the first chapter, it is the first chapter we can read. Before it, there may be a prologue written in particles and fields we cannot yet detect, in moments so close to the origin that our current physics falls silent. There's an old idea in philosophy that to know where we are, we must first know where we began. The CMB is as close as we have ever come to the beginning. And yet, in knowing it, we learn something else. The beginning is not a single point, but a horizon we cannot reach. The more we understand, the more that horizon recedes. This is not a failure of science. It is its nature. The unknown is infinite, and so in some sense is the pursuit. Long after our species is gone, long after the Earth has cooled into a silent cinder, the CMB will still be crossing the cosmos. It will grow colder, fainter, and redder, until its wavelengths are so long they fade into the cosmic darkness entirely. One day, even this last memory of the Big Bang will disappear, stretched beyond detection by the relentless expansion of space. But that day is far beyond us. For now, the light still comes. It still falls on mountaintop observatories and Antarctic ice, still hums in the deep vacuum of spaceborne instruments. It still speaks, and we still listen. The most ancient light, still crossing the universe, does not care for us. It does not need us. And yet, in its indifferent journey, it has given us the greatest gift, the story of our origin, written not in myth or metaphor, but in the language of physics itself. It is a reminder that we are small, that we live in a fragile corner of an expanding universe. But it is also a reminder that the atoms of our bodies, the neurons of our thoughts, and the instruments of our science are part of the same unfolding story. We're not outside the cosmos looking in. We are the cosmos looking at itself. The light began long before us. It will continue long after us. And yet, for a brief moment in its endless journey, it passed through minds capable of wonder. That may not be the purpose of the universe, but it is enough.